In the last video, I talked about substitution reaction. Click here if you haven't watched that. Now we are going to talk about elimination reaction. Elimination reaction is an organic reaction in which two substituents, usually hydrogen and the leaving group, are removed from a molecule. Typically, this will form a double bond. Just like the substitution reactions, there are E1 and E2 elimination reactions. Here is the reaction of third butyl bromide with water to form isobutylene. In E1 reaction, only the substrate in the reaction affects the rate law. Changing the concentration of the water as a weak base in this reaction doesn't affect the reaction rate. The mechanism is stepwise. Firstly, the bromine leaves the molecule forming the carbocation. Then, water removes the proton from the molecule forming the alkene. Because E1 reaction is a stepwise reaction, it needs a substrate that stabilizes carbocations, such as tertiary carbon, allylic carbon, and benzylic carbon. Here is the reaction of 2-bromobutane with potassium third butoxide. In E2 reaction, both of the substrate and the base affect the reaction rate. The mechanism in E2 reaction is concerted. Here, third butoxide attacks the proton on the molecule, which then pushes the electron towards removing the bromine, thus forming 2-butene. The mechanism of E2 is a good tool to predict the product configuration. If we look closely on the 2-bromobutane reaction, there are two possible alkene products, E and Z alkenes. However, the major product is E alkene. For E2 reaction to work, the hydrogen and the leaving bromine group needs to be in anti-periplanar position. This leaves us in two possible conformations. The conformation with two methyl groups in anti-periplanar position is less hindered. Therefore, this leads to the formation of E alkene as the major product. The mechanism of the reaction makes E2 a stereospecific reaction. By having two different configurations in the starting material, it can lead to different alkene configurations. To explain this, we can draw the starting material, positioning the proton and bromine in anti-periplanar conformation. Then, draw the mechanism here for the bromine to leave the molecule. Then, we redraw the product in the zigzag diagram. Here we get E and Z alkenes. Substitution and elimination reactions are always competing with each other. If we look closely, it only matters where the attack occurs. Attack on the carbon bearing the leaving group leads to a substitution reaction. Attack on the hydrogen leads to an elimination reaction. So in general, strong bases will attack the proton leads to elimination, while weak bases will attack carbon leads to substitution. Using ethanol as a weak base, third butyl chloride will undergo substitution reaction by SN1 mechanism. If we use sodium ethoxide, which is a strong base, this will lead to E2 elimination reaction. Next, the size of nucleophile also the factor of the reaction. To be able to undergo substitution reaction, nucleophile needs to squeeze between the carbon substituents. Comparing the attack on carbon versus hydrogen, attack on hydrogen is much easier. Thus, bulky and basic nucleophile will certainly prefer elimination reaction. For example, the reaction of 1-bromopentane with sodium hydroxide and potassium torbutoxide. Sodium hydroxide produces hydroxyl ion, which is a small nucleophile, thus prefer substitution reaction. Potassium third butoxide, a bulky basic nucleophile, will prefer to attack hydrogen, leads to elimination reaction.